YouTube does say it's waiting for me. All right. I guess first thing, we're wrapping up Module 3, so like the fun logistics of the day. We're wrapping up Module 3. Friday, we built a question for Quiz 3. I'll put that up today by this afternoon. I'll push off, I think it was supposed to be due tomorrow, but I'll push it off. Like, we're champions now, we got time. I'm not gonna build a quiz while I'm watching the game. Like, just, we got it. We'll get there. So I'll push that one off so that there's actual time to get to it. And then I wanted to set up like pendulum experiment today, but I like to do like a 3-story pendulum. So I'll stand outside and like try to measure it, but I don't want to stand in the rain. So we'll do that next time. Today we'll look at like what are we actually doing when we say we're solving this differential equation. What does that mean, and what can we do with that? So that's the plan for today. It's kind of, usually it's measure then predict. Today we're going to predict then measure. Maybe that's a better way to do it. I don't know. That is like the scientific method. Go in with the hypothesis, test it, and then. So I just like to do things backwards. It's just how I roll. So first question is, let's just look at our ordinary differential equation. Our ordinary differential equation of motion, EE. We end up with this pendulum that's theta double dot equals negative G over L sine of theta. Take a second, we either want to look at what does the free body diagram look like, or even like what does the engineering diagram look like? Like what are the constraints? Like what is this thing even saying? I know it's an equation that we can like jump into and start plugging numbers into and we can solve it. But before that, what is it even describing? That's what I'm trying to figure out now. Like when we say this is a simple pendulum, what makes it simple? What does it look like? Yeah.
So it's just the constant times the sine function. You know that the sine function is like this, so it's like the oscillator.
Okay.
Like it'll peak at one point and then it'll dip.
Yeah. So do we have a pendulum that looks like a sine wave?
Yes.
So we have something. It doesn't want to do what I tell it to today. Anyway. So do we have like, if I draw a diagram of it, pendulum is a sine wave?
No.
No? No, something else is a sine. Acceleration is a sine wave?
Or angular acceleration.
Angular acceleration is a sine wave?
You know what theta double dot is?
Yeah, theta double dot is angular acceleration. Some kind of rocking motion, maybe? Cradle. Yeah, what is it like if you draw? Yeah, we can take a second. Again, like all we need is like a bar napkin to get started. When we say it's theta, what angle are we measuring? What does it look like?
The angle from the vertical.
From a vertical axis? Yeah. Vertical. So we need some kind of vertical axis. And then we'll say theta. I'm using right. I like right hand rule. Like counterclockwise positive. So that's our theta. What does the rest of this look like?
triangle.
You're like doing this, right? Yeah. What is that one?
I mean, I assume L is the light, but the
A length. Okay.
so from like the from where it's attached to like the weight of the end.
Okay. So distance from an attachment to a weight is L.
Maybe.
Maybe. No. Don't want to commit to it. Okay. We won't commit. Triangle. Sorry. For sign data? Well, I was trying to figure out, like, when someone says, this is my equation of motion, what does the pendulum look like? That's the equation of motion. Yeah. Okay. Yeah. It's like a harmonic.
Yeah. It goes back and forth the same like distance, I guess,
Okay. Yeah. Alright. So it'll like start at one place, swing down, and end like a mirror of wherever it started. You can take it as a free body diagram, or you can so far in this here's a diagram that would turn into a here's the equation.
It wasn't like you were excited, just like it was
Yeah, that's going to describe like how fast
it was like
the speed is.
oh, it's only
Yeah. Okay, so you think wherever it starts, it's got to end. Okay. How do you know that? You don't. You could say that you know it. Like there's like some stuff.
Yeah, I was just in high school. So you're gonna read our dinner.
Okay.
That's it.
Okay. Yeah. Okay. Yeah, so wherever you just started from, where it can't get past. That's not really okay. Yeah, okay. Yeah, so that makes sense.
just like just because you could just you could do that, but then you would never say
sent a message this morning. I don't think you want me. Yeah, so I was like.
Yeah, okay. All right, so I've seen like a few different things. It's also kind of a weird question because so far we've just been like, okay, here's a picture, make it simpler, and now turn it into like, what are the forces acting on it? Here we're doing the opposite of like, here's the equation, how do we work back to what it's describing? So up top, we have this thing like, that point where we're measuring the angle from, that's some kind of fixed point. Like that's our origin. And I think I saw like some people sort of thinking like drawing something like this. But this is one way for an engineering diagram. Like here's a hinge, that hinge does not move. It has two constraint forces to make sure X and Y aren't moving. And then a big old something or other, right? A cherry down at the bottom that's swinging kind of back and forth. And this was kind of nice. People were drawing like the path of this object of like this object is going to swing back and forth. If it starts at 0 velocity at theta, it's going to swing over to negative theta and then come back to theta. And it seemed like some people felt that way, but they weren't sure if it's true. What do you think? Is that true? That if it starts, if you release it from rest, it'll swing to a negative value and then swing back to where it started? Yeah?
I think it would, as long as you like neglect air resistance and stuff.
Okay. Are we neglecting air resistance? Yes? How do you know?
I mean, it's not it would affect the acceleration.
It would be in our acceleration term, right?
Yeah.
There would have to be, so there's air resistance, there's friction, there's like viscous damping. What are all those terms a function of? They all had one thing in common, like they were always f of something, like some function of something, based on how it's moving, based on the motion of the object. I know these are all like weird abstract questions of like, what is the nature of reality kind of stuff, but.
Was it surface area?
It does, yeah, actually it does, not so much like surface area, but if you want to get deep, like even more abstract, then all of them end up being a function of path. So they're path dependent functions rather than path independent functions. But that's a whole like, now we want to talk about like Lagrange equations and like all the real cool fun stuff that you come back for grad school for. But yeah, they become like path dependent for some reason. But the reason for that is that they're all are
they like all functions of position?
So this one, like sine, when we have this negative g over L sine theta, that one's a function of position. So like based on the angle, if I go to a certain angle, I always have the same acceleration back. So it's just always, yeah, that's just always how it is. The bigger the angle, the more the acceleration. But with drag, damping, and friction, it's always some function of speed. Like there's some, like either a theta dot or an x dot or a v, like something, somehow like the faster I move, the more energy I lose. That's not in our differential equation. So this is always going to be some kind of harmonic motion. It might not be a sine wave because we have a nonlinear kind of equation of motion, but it's always going to be harmonic. If I start at theta, I'll end at negative theta, and I'll come back to theta. Kind of. Yeah, so on that little cherry, we have like, and I saw this diagram, an mg and a t, right? Like some kind of tension, some kind of gravity. So like mg going down, pulling it back down to 0, angle 0, t is always perpendicular to our motion. So it's never changing the speed of our object. It is like all forces create acceleration, but it does not change the speed. Remember we had like a dv dt and a v squared over r. T is always a v squared over r relation. So it's always creating centripetal acceleration, not increase in speed. At least because r is constant. If r was changing, it would be a different story, but it's not. All right. So that's at least for a pendulum, like a simple pendulum where we're just considering tension, gravity. Theta double dot is negative g over L sine theta. The linear solution is that sine theta is theta. Is that good or bad? Why do that, I guess? Why would I want sine theta to be theta? Does that help?
Is it like if theta is bigger and the acceleration is bigger, if theta is smaller then the acceleration is smaller?
Yeah. Is that different for sine theta?
Not sure.
Yeah.
Sine is like 0 sine 90 degrees is 1.
90 goes to 1. Yeah.
It's the same.
Yeah. Sometimes it's exactly the same. Like if theta is 0, sine theta and theta are both 0.
Well, what if it like exceeds? I'm just thinking about the unit circle.
Yep.
The pendulum's only be like 30 degrees. Theta wouldn't really exceed like 30 degrees.
Yeah.
So that would be pretty much the same.
Yeah.
Is this for a small angle theorem?
Mm-hmm. Yeah, so we're using small angle theorem to take a nonlinear equation and turn it into a linear equation. So I think one of the first things that we talked about was like, oh, it's going to have some kind of sine wave, right? Like it's going to go over here, then it's going to swing back over here and back over there, like a harmonic oscillation. That'll be like an exact sines and cosines if it's a linear approximation. So if we say theta is sine theta, the solution is sines and cosines. I'm gonna pull up like actual project, so module 3 in NanoHub. Let's go back up to the top, just do a restart. So run the first one. And so if that's our differential equation, the solution to that differential equation is always like our initial angle is our cosine amplitude, and our initial speed is going to be that sine amplitude. It kind of makes sense because like cosine has a 0 slope to begin with, but it's equal to 1. So the bigger the angle, the bigger the cosine. But meanwhile, sine has an initial slope, but its value is 0. So it's telling you initial speed. So like what is the slope of that sine wave at time 0? And we wanted to look at, was it like 30 degrees? Was that the thought? It was like, is that a small angle? No? How small is small enough? If we want to say like sine of theta is theta, then these two equations are the same equations of motion. 8? 8 is good?
But yeah, I think the TA said that you usually would use it below 8 degrees.
Oh, below 8?
Yeah,
Yeah, okay.
or 8 or below.
8 or below. That's small. That's fine. That's what we said. It's a small angle approximation. All right, so then I'll do the rad to deg of 8. I mean, you can also multiply by pi over 180, but. Oh. Oh yeah, deg to rad, right? There we go. All right, if my initial speed is 0, I start at 8, I go to -8, I come back up to 8. I'm just looking at two waves of like, start here, swing over there, swing back, thinking about like, what is this thing actually showing me? And that's fine. Have you seen like numerical solvers for differential equations? Have you seen this before? Like setting up state variables and saying like, hey, Python, integrate this for me, or MATLAB, any of those? Maybe first time? First time? All right, it's dangerous to go alone. Take this numerical integration scheme, because now we have it. The weird thing about like telling a computer to solve a differential equation for you is that computer is always expecting a first order differential equation. So first step, since we have second order, split it up into 2 first order equations. So I have 2 variables that describe where this thing and how fast it's moving is, theta and theta dot. And if I know both of those, then I know the acceleration of this thing. And my initial value is always some like theta and theta dot. So now my first equation is saying that the derivative of theta is theta dot. Not very exciting, but it is a formal definition. My second equation is that the derivative of theta dot is theta double dot, and that is my equation of motion, where it's negative g over L times that sine of my first input. So in Python, it looks like this, where I've got like dx0 is x1, dx1 is now that g over L sine x0. And if I wanted to add other terms, like I could add like a negative c times x1 squared if I wanted to say like there's also some kind of like drag on this thing, but we're just dealing with like a simple pendulum. Just an ordinary simple pendulum. You don't really have to worry about like the internals of this, but I wanted to at least say like, hey, this is how you do it, and you can just run the code and you'll get a result even if you don't understand what it's telling you. But now but you know what it's telling you. You might not know like how it got there though. So a little bit of black box, but you can look under the hood. Okay, so once I have that function, like pendulum here, that's the one that was those 2 differential equations. I'm telling Python like, hey, solve this initial value problem, IVP, initial value problem, solve it for me. I want to go from 0 to this max time. I want to have an initial angle with 0 initial speed, and then give me, wherever my linear solution had answers, give me answers at those times. It never gives you a function. It always gives you just a whole bunch of numbers. Like this is angle and speed at this time. But that's okay. We're engineers. We like numbers. So we can plot the numbers. We could print them all out into an unreadable table and then start doing linear interpolation if we want, just for fun. All right, so we go from 8, go to -8, back to 8. It's exactly what we said should happen, right? And now we can compare the two. A blue curve is linear, a red curve is nonlinear. What do you think? Is there a difference between the two? At least in this graph? No, you can't even see the blue curve because it's under the red curve. So 8 is definitely small enough. -8 to 8. How big can you go? Like how is 8 like if it's 9 degrees, no good. It's no longer a small angle.
Can you try it?
We can try it, yeah. Do you want to try 9 or do you want to go bigger?
Let's try 9.
9 first? Okay.
Just to see if it like goes it up.
Okay. I'm just going to run through and get to the same graph. Enter, 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 enter. We'll shift enter. Any difference? So maybe 9 is also a small angle approximation. Or no? It seems small angle-ish, right? 9 is small. That's what I was saying. 8 is small. 'Cause 20? I like 20. Yeah, try to do like, so I'm just like increasing that initial angle, right? I'll just run through. Now is there a difference?
The smallest.
The smallest of differences.
Does it depend on the length of the pendulum?
The length definitely changes. I mean, it changes both of them, right? But if you have two pendulums that are the same length and you're just comparing like different angles, then they should be the same if it's a small angle approximation. But here I have, because I have L defined above. So if we made this like a 5-meter pendulum.
Yeah, would that throw it off more or make it more accurate?
Yeah. So I just made it 5 times longer, but it's still going 20 to -20 for linear. And all I really did was change that x-axis, right? Like I know I didn't have you like measure it before. Before, by 2 seconds, we had done 1 period. I think the period ends up being like 2.01 seconds or something like that. Now it's more like 4 point something, like a little over 4 seconds. So the longer the pendulum, the longer the time period. But it seems still pretty small, right? Or no, I don't know. Do you see a difference yet? Yes? How big? What's the difference? Less than a pixel? Or a pixel? A couple of pixels? I don't know. It seems hard to measure, right? At least I would think so. All right, but let's keep running and look at copy this. So I just want to put all 3 of these together. So now I have like all 3 of these kind of states of this pendulum. Where it is, theta dot is how fast it's moving, and then theta double dot is the acceleration. Is there any difference between all 3 of these curves? I don't know. Yeah.
gonna say, it kind of looks like well, the acceleration curve is kind of like the inverse of the position loss.
Oh, yeah.
It makes sense since at the bottom of the, I don't know what to call it, at the bottom of the pendulum, like when it reaches the bottom position, it's gonna be going the fastest.
Yep. Okay, yeah, so here, like if we know that theta, sine theta, or sorry, the theta double dot is negative g over L times theta, right? So they look like the same curve because they should be the same curve, at least for a small angle, for small angles. All right, I'll let you figure out your own. Part of this is figuring out like what is your own rule of thumb for what a small angle really is. I use like 30. So I can't even measure most of the differences anyway. But 8 works. 8 is small. So I'll let you do that. When are things going to get really wacky? How big of an angle do you want to put in there? 50? You think 50? 84? 50? 50 is too, like... All right, let's try 50. What's different and what's the same? Red curve, blue curve. Blue is linear, red curve, non-linear. What's different?
The red one starts to stretch out.
Okay. What's the stretching out? What is that called?
It's a deceleration.
Is it decelerating?
Is this what, yeah.
What do you think? What's the same and what's different? Some stuff is the same, some stuff is different. What do you see?
Let's see the, the height of the thing is the same, it's the same, but it's
Max min?
yeah.
Max min.
But where
The amplitude?
Yeah, the amplitude, but the time is sort of extended.
What time?
It just takes longer.
Yeah,
for-
Some period.
Yeah.
Time period. Time
Yeah.
period? Okay,
Yeah.
alright, nice. Actually, let's run through these. I'll grab this one. So amplitude in both of these, it doesn't matter. Linear, nonlinear, it's the same amplitude, right? Wherever I started, that's where I end the negative value, and then I'm gonna go back to where I was. And then the thing that we're kind of noticing here is that there's a nonlinear time period, and then there's a linear time, that the two time periods, there's some error between those, right? One of them was 4.7 seconds, maybe the other one's like 4.5 seconds, something like that. But there's a measurable difference in time period for larger angles.
Can you remind me what the red line and the blue line are?
Yeah, that would help, right?
So red is sine theta.
Yeah. just writing s theta, or like sine of theta. So adding that nonlinear term starts like stretching it, it like moves it out.
Well, it looks like it's affecting, like, it's not accelerating as quickly, the nonlinear one.
Yeah.
So it's just moving slower. I guess.
Okay. So are you saying like in this curve?
Yeah.
Like down here?
Yeah, like the peak of the acceleration is just higher for the linear one.
Yeah. Okay.
Going back and forth.
So down here we are seeing a difference. Why am I doing that? Oh. Like the peak of the acceleration is different between the two. So now we can start seeing like, all right, why is this time period different? It's like, well, it's based on acceleration. That acceleration is always its max acceleration is always a little bit smaller. All right, so let's do something extreme then. Make a prediction, see what happens. What happens if I take this pendulum and I turn it all the way upside down, 180 degrees? It's not going to move? Yeah.
It's based on like the arm is a solid arm or like it's on the string.
Yeah. Did we set up anything to say like our equation of motion is a string or a solid arm? Which one did we assume with our equation of motion? Solid?
If it's a string, then it can like this string can like bend a little bit as it's like.
Okay.
And like if we did it in real life, maybe it wouldn't, but like mathematically we would have to account for that.
Oh, okay. You think like even in the bottom part, string versus rigid is different?
String, there's more like flexibility within the string itself, so it might like swing, but then like I don't know how to explain it without like an actual string.
Yeah. Yeah, I mean a string has its own mass and momentum, right? So it might have waves.
But we use solid arm for the assumption.
Okay, so we had like a solid massless arm thing. So if it's upside down, then the arm won't let it fall. At least it won't let it fall straight down. Will it swing? No?
It's the same thing as if it was at 0 degrees.
Okay. All right, so it's not going to move. Our linear solution says it's going to move pretty damn fast. It's going to start at 180, and in one time period, it's going to swing all the way around and get back to negative 180. Is that right? I mean, maybe not physically right, but
That's what the code and the map checks it out.
yeah, at least from a small angle approximation at 180 degrees, that's exactly what you would get, because the bigger the angle, the faster it's going to spin back around, and that's just how it goes. It's almost like we put a spring on there, and the spring we stretched it way out and then launched it back. It's still going to have the same time period and still going to get to the same min max. Okay, so now let's see what happens nonlinear. So we integrate it and we end up with this. Did it not move, or is it moving? It's moving. Moving, not moving. Seems like it's moving, or just like. it looks like it wants to move. Something's happening.
Is that only a little bit if this one is the -11?
Yeah. I don't like particularly love like the adding to the y-axis, but it's one way to do it. So these numbers on the side are all multiplied by 10 to the -11. So this is saying that it's 2 times 10 to the -11 degrees. Pretty small, right? And add that to 180. So it's 180 degrees plus or minus maybe like 3. What is that? 3 nanodegrees? Or no, 10 to the -9 is nano. So 3 pico, maybe like 30 pico degrees. So when we do an actual comparison, that thing, it's not going anywhere. It's just sitting there. So we're just looking at kind of round off error, a little, like some kind of like computer numerical error. But it gives us a sense of like how accurate is this thing. It's like pico degree accurate for our numerical solution, at least for 8 to 9 seconds in this, or 2 time periods. Yeah, and sure enough, 0 acceleration, 0 speed. That like it's just not moving for the most part. Yeah. All right, so let's go back. I'm gonna turn this back to like 60. This is like kind of halfway between. So now we have like a little bit of difference, but it's back to like what it started as. If you're So we talked a little bit already about like how do we describe the differences or the similarities. We're looking at waves, so we can describe it with time periods or frequency, amplitudes. Like those are great ways to compare these outputs. So that's kind of like these first 2 questions. Where do you see the biggest differences? Like, is it in the position? Is it in the acceleration? And then when you quantify that error, when you say there's a difference, what is that? What are you measuring as that difference? Are you saying the amplitude is different? How big is it? Is it 0.1 radian per second squared, or is it 10 radian per second squared? So then the last step that we haven't talked about is like, what else could you measure? Like, what else could you compare between these two? So we have theta, theta dot, and theta double dot. What else? What other things might you care about of like physics of a pendulum or engineering, like engineering design of a pendulum? What do you care about? I don't care about pendulums. I only care about springs and masses. Just trying to design suspension for my hot rod. So examples could be like, in all of this, we never talked about tension. Like, what's the difference in tension for linear versus nonlinear? Is it the same? Coming back to here. Do you remember what the equation for tension was? Because we ended up with our equation of motion, but then also there's like some equation for tension too, right? To say this is some constraint equation on like how does tension get affected. Yeah, so it's the other component of mg, right? So tension was mg cosine theta plus ml theta dot squared. what is a linear approximation for cosine theta? Theta? 1?
That's really close to
When if it's real close to 0, cosine theta is 1. What about theta dot? If theta is real small, how big is, then theta dot also has to be pretty small, right? Because even if you go from one side to the other, you're not moving that far.
Well, if you're, it's also depends on time though.
Yep.
So it's the same. Theta dot would just be theta dot. Because even if you move like a small distance, you also live in a really small amount of time.
Yeah, well, we already know the time period is something that's not really small. So we know that delta t is not as small as theta.
Okay.
So theta dot should be pretty small, and if we square it, now it's really small. So plus 0. So at least for if we're doing like a linear first order approximation, tension is always equal to gravity. Versus the actual equation, mg cosine theta plus ml theta dot squared. Those are very different. I mean, they could be very different. In the case of that 180 degrees, like, yeah, now we're talking very big differences. But even something up to like 30 or 60 degrees, something bigger. This is kind of like next, if you want like a preview of what's coming next. If we think about like how much kinetic and potential energy this pendulum has, it has mgh of potential energy and then 1/2 mv squared of kinetic energy. So we could say 1/2 m L theta, well, L squared theta dot squared plus mg L 1 minus cosine theta, and we'll do like 1 and 1 equals 1/2 m L theta 2 squared or we could calculate like mgh and v and add them up. And we could look at like what is kinetic and potential energy over time. And if we add them up, they should always be some constant value, at least based on conservation of energy. Because we didn't include drag, there's no friction, there's no damping. So all of our energy is always either kinetic or potential. At least that's what it should be. For a linear approximation, that's not the case, but it should be that. All right, I was talking for a while. Normally I like to like check back in, but I guess this was like the tour. Behind this door, now this. So let's cut it there. So next time so this is like some mental homework. There's no like actual written deliverable, but we do need to be prepared. We're going to look at pendulums moving just in a classroom. So think about like what is an accurate way that you could make a prediction and also measure something about the pendulum moving, and you can make a comparison between your prediction and your measurement. So think about that. Like, how do you do an accurate measurement so you can compare it to something that we can calculate? That's what we're going to try next time. Sound good? All right, cool.